Hello again, physics guys. We're talking about torque. This is part 3 of chapter 13. Or no, sorry, chapter 12. Yeah, chapter 12. So torque is to rotation as force is to linear stuff. Just like F equals ma. So force is what makes a particular mass accelerate. Tau is equal to I alpha. So a torque is what causes something that has a rotational inertia to accelerate with an angular velocity. All right, sorry, with an angular acceleration. All right, torque also equals force times distance, but I have to qualify this. All right, this is going to be a little bit tough to explain, I think, but I think by the end it'll be a good thing and you'll understand it. So tau equals F cross R. That's a cross product of two vectors, and you don't know what that is yet, but I have trouble remembering what this kind of stuff is and does. It's kind of a formula. What I remember much better is that the force and the radius, to calculate the torque, the force and the radius must be perpendicular to one another. If they're not perpendicular to one another, then you've got to find the component of the force that is perpendicular to the radius, or you'd have to find the component of the radius that is perpendicular to the force. I'm going to show you both ways here. So if this is the case, I would want to make this into a right triangle, and see this component of the force is parallel to the radius. It's not doing anything to turn that screw. This is the component of the force that is perpendicular to the radius. So I'm going to say it's F perpendicular. So tau equals F perpendicular times R. This sign here is supposed to mean perpendicular. All right. What I mean by that is this is the component of the force that is perpendicular to this radius. All right. So that means we only care about this component of the force. All right. Now, we could redo that a different way. We could also say that instead of finding the component of the force that's perpendicular to the radius, there's another way to do it. You could also find the component of the radius that is perpendicular to the force. So, like we're making this triangle here so that this is the component of the radius that is parallel to the force, but this is the component of the radius that is perpendicular to the force, R perpendicular. So that's another way we could do it. Tau equals F times R perpendicular. And by that, I mean the component of the radius that is perpendicular to this overall force. So this is what I usually try to remember, and sometimes one way is easier than the other depending on how the whole situation is set up. There's probably another way to do it, maybe with this cross product that I always have trouble remembering, but maybe there's an easier way even than what I've said here, but that's just harder to remember, where you involve the angle phi and you do like F times R sine of phi or cosine of phi or something like that. Or usually I think of this as being the angle, this theta here, and whatever phi would be, if it was sine or cosine of phi, it would be the opposite cosine or sine of theta. Let's move on and find out more. So yeah, so here it is. So RF, torque, is defined as R, so that's the magnitude of the radius times the magnitude of the force. So that's overall radius, overall force, times the sine of phi. And you have to remember then what phi is. That phi is defined this way. So, but I think it would be the same if we said RF cosine of theta if we make this be theta. That should give you the same, at least the same magnitude of the value of torque, if not the same sign. But we can always figure out our sign for torque, SIGN, by just defining counterclockwise as positive and clockwise as negative. So this force would produce a positive torque. All right, the SI units for torque are Newton meters. English units are foot-pounds, so feet would correspond with meters. Pounds is a force that would correspond with newtons. The ability of a force to cause a rotation depends on, obviously, the magnitude of the force, the distance that the force is from the pivot, and the angle at which the force is applied. All right. These two forces cause a positive force. This one that's at a right angle will be the way to maximize the torque that that particular force can do. These two forces would be a negative torque, would cause a negative torque. These two forces would cause no torque at all. And you could kind of see why, but also just because the sine of phi between them would be sine of 0, or sine of 180, which would both be 0. All right, in practice, torque is often calculated using the moment arm or lever arm. So I think they're showing here what I was saying earlier. So it's distance times force, but that is only the absolute value. You have to provide the sign based on the direction. What is the sign of tau here? Obviously, it's positive. So D, they're saying D is this, what they're calling the moment arm, which is what I called R perpendicular. And it's the component of the radius that is perpendicular to the force. Okay, here's a quick check. There's this object, and there's this force right here, and a force right here. It wants to know what force at P will cause the net torque to be 0. In other words, we'll keep this thing from rotating at all. Have you guessed it yet? I think it's A. Why is it A and not C? Because this force has a larger moment arm, a larger radius, a larger distance between it and the pivot, which gives it a greater torque. So this one's shorter, so I have to have a greater force to counterbalance that, and it's got to point up because this wants to make it turn counterclockwise. So this one has to make it want to turn clockwise, so it's got to point up to make it want to do that. So it is choice A. An example. Lewis uses a 20 centimeter long wrench to turn a nut. The wrench handle is tilted 30 degrees above the horizontal. Lewis pulls straight down on the end with a force of 100 newtons. How much torque does Lewis exert on the nut? All right, so I would, there's lots of ways to do it. Let's just look at the various ways. We could say F times R times sine of phi, which is pretty easy in this case. If we imagine this being 30 degrees, it's kind of like a ramp. Like if we're straight down here, then this would be 30 degrees. So 90 plus 30 is 120, so phi is 120. So it would be 100 times 0.2 sine of negative 120. I think that'll give you the correct SIGN if you put it in like that. But you could just put in sine of 120 and then just give it the correct sign, which might be safer. Okay, another way to do it, Okay, so the next way we could do this would be to do the force times the perpendicular component of radius. So the way this is drawn makes this pretty easy to see. Here's the force. That's the true force, the true direction of the force. So if we get this component of the radius, then that will be that will help us find the torque. So here's my triangle. Here's 0.2 meters. So it's going to be this is going to be 0.2 times cosine of 30. Since this is the adjacent side to the 30, then it's going to be 100 times 0.2 times cosine of 30. And that'll also give us the answer. And here's the third way, which is similar. I could find the component of the force. So here's the true force. And so that true force needs to be the hypotenuse of a triangle, where these are the legs, and where this is the perpendicular component of the force to the radius. Where is the 30-degree angle located? I believe it is right here. Here's the 30-degree angle. And so we can say that force is 100. So F perpendicular is going to be 100 cosine 30, and then the R is 0.2. So that's kind of it turns out to be the exact same stuff, just rearranged. That's how you do torque. Pretty thorough explanation there, I think. Alrighty. Net torque. The figure shows the forces acting on the crankset of a bicycle. F axle, that's the force of the axle holding this in place. That doesn't cause a torque at all because it has no radius. It has no radial distance from the center point, so it will cause no torque. Notice it gives us several different torques, and we would have to do the sum of the torques, and we'd have to, it would be F1 times times that distance there, or times some angle, sine of some angle, or we could get this perpendicular component or whatever, but it'd be F1 R1 plus F2 R2, where R2 would be, if this is pointing this way, I would extend this to find that R2 right there. See how you have to extend the force sometimes? Or I could break this force down and get this component of the force that's perpendicular to the radius. Anyway, you got to do all that, and you got to do that for all these forces, and that will give you the net torque. Why is this pedal able to do such good work, such a useful thing to this bicycle? Well, it's because it has the greatest radius. So the pedals extend far beyond a much larger radius of a circle than the sprocket itself with the chain on it, which is why this is able to put more force than the chain is, or not more force, but more torque than the chain, which is why it's able to. You're able to pedal your bicycle and get some good use out of it. The torque due to gravity is found by treating the object as if all of its mass is concentrated at the center of mass. So we would assume, since this is an axle, that this object is fixed right here. It can't move from there, but it is able to turn because it's labeled as an axle. So what does the object want to do? It wants to rotate according to its center of mass. So what you do is you pretend like every bit of force from this object, from the weight of this object, is concentrated at that center of mass. And then you find the distance from the axle to the center of mass, and you do the same stuff that we talked about before, where you either will find the perpendicular component of the radius, or you will find the perpendicular component of the force. One of the two to calculate that torque. What does the torque do? We've already talked about that. In the absence of a net torque, the object either does not rotate or rotates with constant angular velocity. All right, this is a good little summary chart talking about all the rotational dynamics and how it's completely analogous to all the linear dynamics. All right, quick check. A student gives a quick push to a puck that can rotate in a horizontal circle on a frictionless table. So you're looking down on a frictionless table. There's the push. After the push is ended, the puck's angular speed does what? It says frictionless, so I think it's going to hold steady. Yep. Starting an airplane engine. The engine in a small airplane is specified to have a torque of 60 Newton meters. This engine drives a 2-meter long, 40-kilogram propeller. On startup, how long does it take the propeller to reach 200 RPM? Okay, so this is just, it's like a Newton's second law problem. It would be just as if it said, you give this thing a push with a force of 60 newtons on this mass. What is its acceleration, and then how long does it take it to get to this speed, given that acceleration, which would be, may take some kinematics to do. But we're dealing with torque instead. So instead of F equals ma, it's torque equals I alpha. Now, this propeller is spinning about its center, and I think we can model it like one of those rods that we looked at earlier. Imagine it just being a uniform rod. That makes things a little more simple. The moment of inertia for a uniform rod is, you may want to take a picture or something of this slide here. You may want to take a picture of that so you have it handy whenever you approach problems. But we noticed the rod thing about its center is 1/12 ml squared. So 1/12 ml squared alpha. Now, what is the torque that this engine can produce on this object, on this propeller? It is 60. So that equals 1/12. M is 40. L is 2. And we can solve for alpha. All right, I paused it and calculated it. Alpha is 4.5. 4.5. What are the units for alpha? Radians per second squared. It wants to know how long does it take the propeller to reach 200 RPM. Well, that's a velocity. That's an omega, but it's in revolutions per minute. So let's see here. Let's do that calculation real quick. 200 revolutions per minute. That's going to be 1 minute, 60 seconds. And 1 revolution is 2 pi radians. So that gets us to radians. That is 20.94 radians per second. Now it's doing some kinematics, I think. So omega F equals alpha T plus omega I. Well, omega I is 0. Alpha I know. Omega F is what I'm trying to accomplish. 20.94 is what we're trying to get to. 4.5 is the alpha. And time is what we're looking for. And we're going to find it just by dividing. I won't even go through the rest of that step because it's over. All right. Constraints due to ropes and pulleys. A rope passes over a pulley and is connected to an object in linear motion. The rope does not slip as the pulley rotates. Tangential velocity and acceleration of the rim of the pulley must match the motion of the object. So the velocity of this object equals omega times the radius, which we already know all that. So, all that's just not new. There'll be some pulley problems, I'm sure, which will involve torque. All right. Static equilibrium. All right. Good stuff for mechanical engineers, architects, civil engineers. A lot of people, a lot of STEM people need to know about statics. No net force, no net torque. Sum of the forces, sum of the torques, both equal 0. Important branch of engineering called statics analyzes buildings, dams, bridges, other structures in total static equilibrium. I really enjoyed my statics class at Tech. It was all about what we just said. There is no net torque about any point in static equilibrium. All right, I'm going to tell a joke to break the monotony here. A snail reached an intersection. He stopped. He looked both ways, and he began to go across. All of a sudden, he gets run over by a turtle. He recovers. He appears in animal court, which, of course, an owl is the judge. And the judge says, "Mr. Snail, can you explain to us what happened?" Snail says, "Judge, I really don't know. It just all happened so fast." But all right, I know that was bad, but maybe you laughed at how dumb it was. Static equilibrium. Will the ladder slip? A 3-meter long ladder leans against a frictionless wall at an angle of 60 degrees. What is the minimum value of mu sub s, the coefficient of static friction with the ground that prevents the ladder from slipping? All right, we got a bunch of torques, forces, and all that good stuff. And probably, I bet what's going to happen is we're going to have both equations, the sum of the forces and the sum of the torques. Multiple equations to solve for multiple variables. A system of equations kind of thing in order to solve this problem. I bet that's what's going to happen. Let's find out. All right. Hudson, you're going to love this problem because it doesn't give you it gives you very, very few numbers. I know how you love that. So, anyway, let's do the sum of the forces in the x direction on this here ladder. It's just going to be, I'm going to use the letters that they have already put here for the forces. It's going to be N2 minus the force of friction. That's going to equal 0. Sum of the forces in the y is going to be what? It's going to be negative Fg plus N1, and that's also going to equal 0. So let me break some of this down a little bit. That N2 is just the normal force from the wall on the ladder here, and this N1 is just the normal force of the ground on the ladder here. So N2 minus the force of friction is going to be mg. It's F and mu, right? Sorry, it's not mg. Yeah, it is. It's mg mu. That equals 0. And here, Fg is negative mg plus N1 equals 0. Alright, so in that case, N1 equals mg. And so this would have been N1. This would have been N1 mu, right? Oops, ran out of room. N1, shoot. That friction is N1 mu. But N1 is just mg. We just proved it here, so that's why I wrote mg there. And we are looking for mu. We have too many variables. So we need to go to another equation, which is going to be the sum of the torques. Will help me get a new equation. I'm going to do the sum of the torques about point C. Point C is going to be this point here. That's a good point to choose because that makes two of the forces produce no torque at all, which simplifies things. So the sum of the torques is going to equal Fg. Notice Fg is going to produce what sign? A positive torque. So Fg times what? Times Fg times this perpendicular component of the radius. So that perpendicular component of the radius, if this is a 3 meter long ladder, then this is 1.5, and so this is going to be 1.5 cosine 60. So Fg times 1.5 cosine 60. And then this here produces a torque, and it is going to be a negative torque. It's fighting against that, so that's why it's not spinning. Minus N2, and N2 acts along this line, which would make this right here be the perpendicular component of the radius to that N2. So if looking at this triangle here, if this is 3, my 60-degree angle would be up here. You could do a 30-degree angle here and be fine too, but this is the opposite side. So it's N2 times 3 sine 60, and that equals 0. All right, now let's see, Fg, that's just the whole mass of the ladder acting at that center of mass. We can treat it like that. So that's mg, so it's 1.5 mg cosine 60 minus 3 into sine 60. That equals 0. I'm going to now, notice I got the same variables here. I'm going to solve for N2 so that I can substitute in for this N2. That's going to be 1.5 mg cosine 60 equals 3 into sine 60. Now divide by 3, sine 60. And so N2 equals 1.5 over 3, that's 1/2 mg cotangent 60, right? Cosine over sine. So now this thing is going in there. And I need some more room, so I'm going to just, what can I do? Let me figure out how to erase all that the easiest way. Right, my answer at least 1/2 mg cotan 60 is going there. Let me erase a lot of this. I'll pause it while I do. Okay, so putting that in there, we get 1/2 mg cotangent 60 minus mg mu equals 0. Look what happens here, Hudson. What's going to happen here, Hudson? Say it, man. Say it. The m, we can divide everything by m and everything by g, and the mg's go away. That's why they didn't have to give us the mass of the ladder. So that just leaves us with, I just moved the mu over, moved the mu. And so I got mu equals 1/2 cotan 60. That is crazy, isn't it? Pretty amazing. Let me see if I can get that as a number here. 0.5 times 1 over tan 60. 0.289. 0.289 should be the answer for mu. This is the minimum value for mu that would allow the ladder to not slip. That's really cool to me that we can figure that out. I hope we got it right. Come on. 0.29, isn't that what we got? .29. I think that's what we got, isn't it? Let me make sure. Yes, it is 0.29. Excellent. Woo! Balance and stability. I'll stop right here and we will do another part for the video.